Welcome to my new calculus channel. My name is John Gabriel. And in today's video, I'm going to be talking about Euler and his elements of algebra. Forgive me if I pronounce his name sometimes as Euler, but the correct pronunciation is Euler, and that's how it's pronounced in German. But before I start on that, I want to remind you that I've actually compiled a series of lectures, as you see over here. Just let me shut the camera so that I can speed this up a little bit. Right. Okay, so I've compiled a series of lectures on my new ebook, which consists of about 13 chapters. And it's the most important book ever written about mathematics and calculus. Nothing that has come before this book. In fact, all the calculus books and all the mathematics books combined do not have the same worth as this book. And it's only 123 pages or something like that. So I encourage you to read the book. And there's a link to the book in each of these chapters, and study it if you're really interested in understanding mathematics and calculus and well-formed concepts. So with that being said, let me continue now with the discussion of Euler's elements and some of the theory that one finds in the IB curriculum, which was designed in Switzerland. I've actually taught the diploma level curriculum in China, and it's a little ironic because the ideas that are propagated in such a course, let's just go to it over here, are really a bunch of rot. And so TOK actually stands for the theory of knowledge, and this is what it says: as a thoughtful and purposeful inquiry into different ways of knowing and into different kinds of knowledge, theory of knowledge, or TOK, is composed almost entirely of questions. It's composed almost entirely of questions, and some really stupid questions. And the dumbest of these is the central one, which is, how do we know? Well, let me answer that particular question very quickly, because everything else that comes after it is answered by this. This is how we know what it means. This is how we know what we know. If the knowledge that we have realized is based on well-formed concepts, then we know that it is sound and reliable knowledge. And before I came along, there was nothing in academia to help a learner or anyone else who is interested in determining if a concept is well-formed or not. And in this article on LinkedIn, I give you a 4-step method to determine whether a concept is, in fact, valid or not, or well-formed or not, excuse me, or good or bad, right? So when I say a bad definition, I really mean ill-formed. When I say a good definition, I mean a well-formed definition, generally one that can't be rubbished. So that's the answer to that first question. And then, so we get more questions here. What counts as evidence? Well, obviously, proof counts as evidence for X. And what is that proof based on? It's based on well-formed concepts. Now, there is nothing in the theory of knowledge that compels me or anyone else to accept someone else's ill-formed definition. Think about that. I do not have to accept a definition in order to prove it wrong. All I need to do is show that that definition is ill-formed, okay? And so I'm going to show you very quickly that one of Euler's definitions is ill-formed. And let's just take a quick look at it. Let's just get this out of the way here. Right, so Euler said in his Elements of Algebra, daher ist unser Bruch, that means therefore is our fraction, this fraction, gleich dieser unendlichen Reihe, equal this infinite or unfinished series, okay? And this is a series. So what he was saying there is that the limit, which is this fraction, is actually equal to the series, even though it's impossible to sum such a series, okay? Because even if you could live forever, you'd never be able to sum such a series. And there are a lot of problems with this definition, major, major problems. You can read all about them in my article here. One of the fallacies that arises out of this definition is the definition of 1 as 0.999. Now, you know, there is not a single proof. There's not a single proof that 0.999 is equal to 1. First of all, this here is not a number, okay? It's not a number of any sort. So, and there is nothing to prove because Euler defined it as S equals to lim S, where this here is the series or the sequence. It doesn't matter because the sequence is obtained from the series, yes? So we don't have to bother with differentiating between the series and the sequence. So he is saying that this series or sequence, which consists of 0.9 plus 0.09, etc., all added up, is equal to 1. It's never equal to 1 because, first of all, 1 already has a definition in every radix system, okay? It's the unit. 1 is the unit. Here's the radix. These are tenths, hundredths. These are tens and hundreds, etc. Now, 1 already has a definition. You cannot, regardless of how many nines you put on the side, first of all, you can't go on forever, and they're not all there. And this limit here doesn't care if these terms are there, are all there, or even there at all, okay? So the blundering morons in mainstream academia simply don't understand that this is an ill-formed definition, okay? You cannot simply put 99999 there. It doesn't matter how many nines you put. This value here will always be less than 1, okay? But this particular expression here means a representation of this series. And now somebody might say, oh, it doesn't mean 0.9 plus 0.09 plus, you know, etc. But that is utter bullshit. That is exactly what this means, okay? And then what Euler does is he proceeds to define it. He proceeds to define this 0.9999 as the limit, right? Okay, so, and by the way, this is what mainstream academic orangutans use to define number, which I have debunked so many times. You cannot have 0.999 unless you add these together. In other words, it's a partial sum representation, isn't it? It's like writing down 3.14159 dot, dot, dot. Okay, this here is not pi. It's never pi. Dot, dot, dot doesn't make it pi. Do you understand that? Okay, so this definition is especially laughable when we think of incommensurable magnitudes such as pi or square root 2, etc. And then a mainstream academic will probably turn around and say, "Ooh, but this is the representation of the limit." Actually, it's not. Pi is a representation of the limit, not as a number, but as an incommensurable magnitude, okay? There is a big difference between a magnitude and a number. A magnitude may or may not have measure. If it has no measure, it's called an incommensurable magnitude. In other words, what that means is there is no number describing it, right? So I don't care if you tell me this is what we use to represent pi. It's wrong. This here never represents pi, and there are innumerably many other numbers that have the same first digits in the same m places as pi, right? So it doesn't matter how far you go, it's not pi. What actually happens when we write numbers in decimal radix form? Do you know? Did you ever know? I doubt it. Let me explain something to you. When you write a quarter as 0.25 in base 10, this here is the measure of the number 1/4, okay? Remember I showed you in previous videos that a quarter is the same as this, right? It's the same as 1 unit to 4 units, okay? Written like that, or 1 like this. So this here explains the measure. In other words, we're using the radix system to express a quarter, but there's nothing to calculate yet. There's no division here. So a lot of this confusion came in because of that idiot, Euler, okay, and his cluelessness as to what it means to be a number. So we look at his first chapter here of fractions in general. And you see, this is where the mainstream got most of their ideas from. So he says, since therefore we may form a precise idea of the quotient obtained in similar cases, though the quotient may not be an integer number. Well, guess what? If it's not a fraction, it's not a number. This leads us to consider a particular species of number called fractions. So actually integers are fractions. There is no number which is not a fraction. Did you get that? Read my article on how we got numbers and what it means to be a number, or broken numbers, of which the instance adduced furnishes an illustration. Wow. For if we have to divide 7 by 3, we easily conceive the quotient which should result and express it as 7/3. First of all, 7/3 is the number, okay? There's nothing pending there. We don't have to divide. We don't have to do anything. That's the number. If we want to express it in base 10, then it becomes 2 and 1/3, all right? So it's 2 and 1/3, but unfortunately, you cannot express 1/3 in base 10. In fact, there is even a theorem that proves you cannot express 1/3 in base 10. There is no way to do it. It's impossible, okay? And I've talked about that theorem many times. So he says, so in general, when the number a is to be divided by the number b, we represent the quotient by a over b. No. He's wrong. We don't use that notation. That's come to be the standard thing because idiots never understood the elements of Euclid, okay? Now, so in general, when the number a is to be divided by the number b, we write a divided by b, okay, is equal to a over b. This goes to the top of the vinculum and b to the bottom. There's no division pending here anymore. It's done, okay? If we say 7 divided by 3 is equal to 7/3, we're done. There's nothing more to be done, okay? This here doesn't mean a divided by b. It means the number a compared to b, which is the number which is derived from comparing a to b, okay? So For example, 1 is a number that we derive by comparing 1 to the unit, 2 by comparing this magnitude to 2 to the unit again, okay? So everything is compared to the unit, and every number is a fraction. So Euler clearly didn't have any understanding of what it means to be a number. That's not surprising, because before I came along, I don't believe anyone did. So he continues, and he really begins to get interesting as we proceed here. You can actually download this document or this book for free on the internet, okay? So then he gets to this particular page where he says some really strange things. So let's see. Where on earth is it? 60. Yeah. So here we go. So he says, to express this idea, it's number 82. To express this idea according to the sense of it above mentioned, we make use of the sign, this epileptic 8, okay, which consequently indicates a number infinitely great. Well, there is no such thing as a number infinitely great. There is no infinitely great number. That's just a junk concept. And we may therefore say that this fraction, well, this fraction here is total garbage, because if you write a over b, both of these have to be numbers. This symbol here is not a number. And then look what he says. He says that this fraction is in reality nothing. What he means is it's zero, because a fraction cannot be reduced to nothing until the denominator has been increased to infinity. See, none of that is possible, okay? You cannot increase a denominator to infinity. There is no infinity. Infinity itself is a junk concept, all right? So, and he continues and he says the fraction 1 over this symbol represents a quotient resulting from the division of the dividend 1 by the divisor. You see, again, this does not mean division. The division in this particular case has taken place, right? And so he thinks that when you consider the result of this, what he thinks is a fraction, he thinks it's zero, but it's not zero. You cannot you cannot use a symbol as a number, right? And this here, any number in this form is complete. There's no division pending. When you use the long division algorithm, you're actually trying to measure. You're trying to measure, okay, as I showed you in this example here. So when you say, for example, okay, let's see how to measure a quarter. So we say, a quarter, we say 4, does 4 divide into 0? Nope. So we put a 0 down, right? This is what they teach you at school. And then you don't add a 0, you multiply by 10, okay? You multiply by 10, and then it divides 10 twice with a remainder of 2, right? And again, you multiply by 10, and then you see, it's 0.25. And it turns out that 2 tenths plus 5 hundredths is actually equal to 25 hundredths, right? 25 hundredths, which is reducible to a quarter, all right? That's what it means. So you could do the same measurement. You could attempt to measure this thing here in base 7, for example. So you could say, okay, again, that's 0, multiply this by 7. 4 goes into there, 1. How much is left? 3, right? And 3 multiplied by 7 is 21, and it goes into there 5, and you can see that this pattern here recurs, which means that it's not possible to measure 1/4 in base 7. It has to be finite. You can't go on forever. Now you can easily show that the limit of this, series, okay, of this series here is is 1/4. It's easy to show that, but you can't sum it, all right? And we don't do stupid things like Euler did by saying that S is equal to lim S. First of all, this here is a sequence, a partial sequence or series, and this here is its limit. And you may say, well, what's wrong with doing it in the case of, for example, 1/4? Well, in this case, nothing's wrong with it. But what happens when you can't measure a particular number, such as a third in that series? A third is not measurable in base 10. For any a over b to be measurable in base 10, 10 must contain all the prime factors of b. Otherwise, you can't measure it in base 10, okay, or in any other base, if the prime factors are not contained in that base. There is no such thing as an infinite series. It is an illusion, a myth, okay? So it's very stupid to write a third is equal to 0.333. What is 0.333? It's not even a unique representation of a third in base 10. First of all, it's unfinished. Therefore, it's not even a number. This is not a number. And you may say, well, it's a unique representation. No, it's not. It's never a unique representation. Think about it. If you could sit down and just write down the threes here in trying to measure a third in base 10, you'd never finish. It's not possible to do it, okay? You cannot do it in base 10, just like you cannot measure 1/4 in base 7. You can sit here and add these things up, but you'll never get a quarter. Yes, the limit is 1/4. We know that. We all know that. And that's what the mainstream morons mean when they write something like this is equal to 1. There's nothing to prove here. There's absolutely zero to prove here. The fact that the limit of such a sequence, the limit of such a sequence is equal to 1 is due to the fact that this sequence converges to 1. Doesn't matter if the 9s are all there or even there at all, okay? 0.9 is less than 1. 0.99 is less than 1. See? Doesn't matter, okay? Doesn't matter whether they're all there or not there at all. All we care about is the limit. To define this as 1 is the dumbest thing that was ever conceived by my intellectual inferiors. You know, those mental midgets or orangutans of mainstream academia who refuse to be corrected? Yep, I'm talking about them. Very well. I think I've spent sufficient time with this. Actually, now not all of Euler's book on the elements is worthless. There are some interesting chapters, and he has done some interesting work. So I wouldn't just discount everything Euler did. And I would recommend that if you haven't read this book, that you should read it, because you'll learn a lot from it, okay? And he does do some things systematically, even though his thought processes are a little garbled and not as clear. Well, I hope that you've learned something from my correction of this Euler mathematician, or mathematician in this case, and that, you know, when it comes to the theory of knowledge, as you see here in the IB course, they clearly don't have a clue what they're talking about. They don't understand even what it means for a concept to be well defined, right? So they ask a lot of questions and they have no answers. And they call themselves erudite. Okay, very well. I hope you've enjoyed this little presentation. I'm a little out of breath, so I don't think I can carry on. Maybe in a future video. So click like. Remember to click like. Remember to subscribe. Remember to share this channel with all your friends and students, because there is no way you can truly understand mathematics unless you understand what I'm telling you here, okay? So this is a new calculus channel, and I am the great John Gabriel, the discoverer of the first and only rigorous formulation of calculus in human history. And you know what comes after that by now, don't you? Till next time, Goodbye.